Okay, let's have a look at lab 4. So we want to look at analog to digital converters again, but this time using interrupts. So we're using the ADCs to look at interrupts. There's all sorts of interrupt sources. In fact, if you look at the documentation, it says there's some 240 odd types of interrupt sources. And unlike with the PIC, microchipped, where you will have the different interrupts, and they have on the latest kind of series, they have high priority and low priority interrupts. And so what happens is you can say, oh, this is high priority, and it'll go to a certain address. And so it could go to address 18, and there will be an interrupt service procedure for high priority interrupts. And then you will poll each of the flags to see what interrupt happened. And so you could have a timer and an ADC and maybe a UART. And what you do is you say, okay, I said those were all high priority. I jumped to address 18, and then it's up to you to which flag you poll first as to which one you service first. So if you had you know, the UART was the most important. You look, when you go to 18, the interrupt service procedure says, hey, was it the UART? If so, do the UART stuff. Then you exit and you go back to your main routine. The interrupt flag is there if there was another one, and you go back and then you say, was it the UART? No. Was it the ADC? Yes. And then you handle that. So it's the order in which you poll the various flags at that interrupt. Now, you could just have two. For instance, you could have a low priority and a high priority and set one on to each one. And then if both interrupts happened at the same time, it would handle the high priority one first. The way the ARM does it is it has a separate system called a nested vector interrupt controller. And so the ARM itself doesn't see all the different interrupt sources. This other piece of silicone does. And it will take from the 240 possible interrupt sources, and it will let you prioritize what you want to happen. And then it passes to the ARM the vector table entry number for the interrupt service procedure. And we'll have a look at where that is in just a few minutes. So let's have a look at ADC interrupts. So it says make a project called ADC int. And so you had ADC poll, so you could just copy it over like we did before, copy, paste, change a couple of the names around, and then have your polling ADC all set up. And we'll just make some changes to the way it goes for interrupts. It says use the thermistor connected as before. You should blink an orange LED at a half-second rate. ADC 1 needs to read the internal die temperature sensor also using an interrupt. So you had the thermistor, and we're going to use that as an interrupt, and we also have the internal die temperature. So inside here, attached to ADC 1, there is a temperature sensor. Now, it's not that accurate as far as I can get as much as 40 degrees difference between boards. So it's not awesome that way. But if you read it's 40 degrees and then you have this in a box and it goes up with whatever you're doing, and it's out in the, you know, out in the wilderness in some sort of capacity, and your box goes up 5 degrees, it will be accurate knowing that it changed. So somebody else may have a temperature and it might read 25. And so if it goes, it'll go to 30. That part is accurate. The initial temperature is not calibrated between the different boards. Okay, so we're going to read it. Some of you are going to get 90 degrees in 204, and that's okay. It's not that hot, and some might see differences. But it's more getting two different sources. I could have had you just wire up a pot or something like that. But I do like the idea of the temperature sensor inside because, again, if I'm in an enclosure, and I can decide whether to open vents up or put a fan on or do something to stop it from overheating. Okay. So it says ADC1 needs to read the internal die temperature using an interrupt. Turn on the interrupt. You will need to use the following. So this is an excerpt from our HAL manual. So the 1800 page HAL manual, and we looked at the polling part before, what you need. And so now we're just going to look at what we need here. So it says, start the ADC peripheral using HAL ADC start IT. And so we're going to do it kind of like we did before. We're in the while one loop. We had HAL ADC start, and then we polled for conversion and that kind of thing. This time we're not going to poll for conversion because it's an interrupt. It's going to give us an interrupt and handle it when that happens. We're going to go do something else in the meantime. You could start up the other conversion, for instance, and I also ask you to blink the orange. Technically it's yellow, but it looks more orange to me, so I always call it orange. But so we'll blink that at a ½ second rate. And then at you use the HAL ADC IRQ handler called under ADC IRQ handler interrupt subroutines. We have to kind of find out where that is. The graphical interface will generate that stuff for you. And then it says at the end of the conversion, there is a HAL ADC conversion complete callback function is executed, and it's defined weak, which means it's not there. You can put your own function in there, and I'll show you where that is. And then we can also check to see if you got errors or that kind of thing. And then it says stop, and once again, we're just going to do it in a while one, so we're not going to stop it. So really the difference between what we've done last time and this time is we're somehow going to enable an interrupt, and then we're not going to poll for conversion. It's going to jump to the interrupt service routine when it's done. And then we're going to get the conversion just like before, and then go back up in the while one loop and do it again. It says print your thermistor value and your dye temperature to 1 decimal place on the ITM data console. So we had that printf going last time, and upload a demo or show me in a class by the start of lab 5, and make sure your main.c is renamed to main.txt and uploaded to the lab 4 folder. Okay, so I want to go over to the IDE here. And so what I've done is I had an ADC poll. And so I just did a right click, and I did a copy, and I did a paste, which gave me, and I renamed it to ADC interrupt test so that we could have a look at it. And of course, what it did is it made an ADC, it called this ADC poll because that's the one I copied. So I renamed it to ADC int test, so it's the same. I deleted my debug, and then I did a project clean. Okay, because I want to make sure that it doesn't have any of the poll stuff still there, some of the object files and things, and that will let you be able to use ADC int. So if I look over here, I've got my thermistor from before, and I also want the thermistor. What was it? What ADC is it attached to? You remember? So ADC3, yeah. So, and this is another thing I'd like to just point out. Let me pull it down here for a sec. Okay, you have to make sure that if I want ADC3 input 11, that is just selected and that you don't have anything else selected in there. You can accidentally have GPIO analog or something else selected. It will let more than one thing select, and it kind of messes things up and things don't work and you don't know why. Okay, so make sure it's just the ADC3 input 11 that we have selected. And then I want the internal temperature sensor. Where did we say that was? Any ideas? Over in ADC1, if I scroll all the way down, there's temperature sensor channel. So it's attached to ADC1. And if we look at that graphical picture that shows the arm up top and shows all the buses and shows where the ports are in the ADCs, it shows the temperature sensor attached to ADC1. And so to go and read that, it's a simple matter of just checking that off, and that will say, okay, that you're going to use it, and then it gives you some parameters in here. So I've got an ADC3 and an ADC1. So over an ADC3, if I look, that's input 11 is selected, and it is because that's what we selected over here. Okay. So as far as making things to be an interrupt, you see over here, there's a bunch of selections. So it's ADC3, and I've got my input 11. And let me just pull this up a little bit. And some of the different parameters. One of the things I can set, for instance, is my resolution. And typically I want my 12 bits, my 0 to 4095. And there's a certain amount of bit times. It's actually 1 time per bit plus 3 for collecting the data off the sample and hold capacitor. And so we'd have 15 clock cycles to be able to go and grab some data. Some of the other things, so I can do a drop down and say, you know what? I wanted to take, instead of 15 clock cycles, I wanted to take 6 clock cycles for that, and plus the 3 for the sample and hold gives you 9 clock cycles. So I could do it faster, but only have 6 bits of resolution. And so you get options to do that. Maybe I don't need it to be as accurate, but by default, we just kind of leave it there. Data alignment, it's going to give us our 12 bits, and we can put it in a 16-bit result. And do I want to right justify that or left justify it? By default, you want to right justify it. But it gives you the option. There could be some reason that you don't care about the lower end of things. You're more interested in the magnitude. So you left justify it and just grab the most significant byte or something like that. Yep.
If we wanted to, could we read the internal temperature and the thermistor both on ADC1, just different channels?
Oh, yeah. Yeah, you can. That's and when we talk a little bit more about that. In on any one ADC, I can set up 16 channels and take my turn to go through. And the next lab, you're going to set up DMA and you're going to move everything over to ADC1 and read both in and have it do it all automatically. But I can have 16 different things on one ADC. And in fact, I can say, read input 1, input 3, input 5, input 1, input 11, input 1, 16 times. I can hop back and forth and have it cycle through that. Not only that, but that's regular. I can then say there's a more important, and in the data it talks about injected channels. You can have 4 really more important that you want to hop in the middle of it doing those 16 channels, do a different 4. So it gives you, there's so many different options. One of the things that lets you do is say we have 3 ADCs, do a sample and hold, start the conversion, immediately do a sample and hold on ADC2. As soon as that starts a conversion, do a sample and hold ADC3, and you kind of daisy chain them to try and get a better sampling rate than you would normally with 1, because you have 3. So you can do those kind of things. And when we look next week at doing some DMA, some of this stuff about scan conversion, continuous conversion, we can have it hop through those different channels and automatically convert things. Okay, but we'll not do that just at this. But there is so many options that you can do with this. So it says the regular conversion and injected conversion stuff is about me having just my regular up to 16 channels. Injected channels say this is more important and I can interrupt these. So if I had this on ADC3 and this injected on ADC3, it would stop those, go do these on whatever channels you selected, and then go back to these. Okay, that's all of these priority things. But for what we want to do right now was just set them, they were on ADC3 and ADC1. And you look at, there's some user constants. I don't have anything here. GPIO settings, PC1 is ADC3 input 11. And so it says my user label is thermistor. And then if I look at NVIC, nested vector interrupt controller. So all I need to do to generate the code to allow interrupts to happen and enable it is to just click on enable. And so if I do that there, then I'm going to go over to ADC1. And ADC1, I had my temperature sensor, and it is selected because it says it's one interrupt, ADC 1, 2, 3, global interrupt. Okay, so by having those two there and saying an interrupt, if I go save and generate code, it's going to put code into my interrupt service procedure um, code location. And so it will be under source, there's a STM32 whatever IT.c file. Okay, and it's been there because when you do a how delay 200, it goes to an interrupt there, and we'll talk about that coming up. So let's just have a look at main. Okay, so I've got, that was my old poll for conversion. And if I go down to source and look at this it.c file, I'm going to double click. Some of the stuff you'll see here, if I go through, it's got the typical header stuff where you put private variables, all of this. It's got, it's put in ADC handle type def, HADC1, HADC3. So we had ADC1 and ADC3 selected. And then it says interruption and exception handlers, non-maskable interrupt handler, hard fault handler. So these are kind of non-maskable interrupt. You hit reset. Then you have the hard fault. So I asked it to go to something that didn't exist, doesn't know what to do. It goes there. And most of these just get stuck in a while one. You could have them turn on lights. Mem manage handler. I had some going to a memory location that didn't exist. Some of this different. Debug monitor handler if I wanted something special to happen with a debug. Now the systic handler, that's the very kind of last of the regular interrupts that can be handled without the nested vector interrupt controller, and it increments a tick. So when we set up our clocks, it set up a timer called systic, and it's a system timer, and it gives us a 1 millisecond interrupt. Okay, so when you go HAL delay 200, it gives you 200 milliseconds. If I go and change the clocks from 168 megahertz to 40 megahertz or what have you, and I go HAL delay 200, it's still going to delay 200 milliseconds. It's worked out the difference to make systic give you a 1 millisecond system-wide tick. Where that can be handy is if I set up a real-time operating system and I have different things happening. Because currently what happens if I go a HAL delay is I just sit there for 200 milliseconds. In the Arduino world, you had there was a non-delay blink example. I don't know if you really looked at it. You could just delay and sit there, or you could have everything else running through your code. Maybe when you did the 7-segment displays, there was a way of not delaying. Okay, and so it has this operating system hiding in behind that will do other things while you're doing a delay. This does the same thing. We have a HAL tick, and if I put an operating system in there, when I do a delay, it gives the operating system permission to go do other things, okay, and then come back. We'll look at that a lot more when we look at in the Linux course, and we look at operating systems in more detail and things like that. Thing here is every 1 millisecond you're going here. Okay, so what you could do in here is you could put a count, and you could say when my count goes to 500, I know half a second went by, and set a flag. And then in your main routine, when the flag is set, clear the flag and toggle a light, for instance. That's one way you could do it and not delay when you're going and running things. In this time, we could also maybe do a HAL delay. Okay, so that's the systic. And then because I put in, check the box on the ADC interrupt, it says peripheral interrupt handlers, and it's just generated this. It says void ADC IRQ handler, and we had ADC1 and ADC3, so it put the handlers for ADC1 and ADC3 specifically. And so if I look in here, in fact, I'm going to go and let's do that. And we'll go open declaration. So there it is there. So there's the HAL ADC interrupt handler. It gets the address for which ADC it is. Currently we have ADC1 or ADC picked off. These assert parameters are making sure that you've got the right thing selected. If you were doing GPIO ports, for instance, it knows they're 16-bit ports. It checks to make sure that you didn't put 32 because it only has a 16-bit port. And then it will give you some little warning messages, go, are you sure you're doing the right thing? And so it has some of this. If I scroll on down, what I am looking for, uh, where is it? I'm looking for a conversion callback, if we can go and find it anywhere. Registered callbacks. It's almost there. That's injected. We don't want that one. I've gone past it here. Oh, here we go. So what the documentation said is if when it called in the it.c, when it called here, as part of this in the ADC, it calls this HAL ADC conversion complete callback. Okay, and our documentation kind of said that. It's going to call HAL ADC conversion complete callback. Before they gave you that ability, what would happen is I am in here, and right in here, I would have to say, okay, what did you want to do? HAL get conversion. Okay, because you jump there means the conversion's complete. You need to get it just like you did last time. Okay, so you'd have to put it in here and you have to grab your value, in which case up at the top, you'd have to make a variable go be external, whatever result, what ADC result external, and over in main, have a global and say, uint32t HAL ADC result or something like that to make it all match up. And they went, you know what, when people have are using interrupts, it's going to go here. We're going to handle all the stuff, see if it's injected channels, see if what all is involved. And then as part of this, it's going to call that HAL conversion complete. And it's defined as weak. And so it's saying, hey, it's a placeholder. I don't have one, okay, but you can use it. So I can copy from void all the way to the end and put it in user begin 4, user end 4, and stick it there. So as a result of your conversion, as a result of the interrupt handler firing off, it goes to it.c, it runs the ADC IRQ handler, and as part of that, it calls HAL ADC conversion complete callback, which you can drop in user begin 4. And what do you want to do in there? You want to get your conversion. You know it's there. Okay, and so I would copy this, right? And you just copy that, and you go to main, and you're going to go down to user begin end 4, way down there somewhere. Well, I got lots of stuff in there from that. Where's it? There we go. Okay, and then so you'll go and so as a result of it firing, this is going to run. So in there, you go, my ADC result equals HAL ADC get conversion or what have you, and that will run. Now, it takes an instance, for instance, HADC, it passes in the address of either HADC1 or HADC3, because you have two different ones going. So you could go something like, if HADC is equal to the address of HADC1, do something, otherwise it's HADC3. So you could do something and know which one fired, because they both go to the same interrupt, right? So this is saying, I don't know what the instance is, I'm going to pass it. So right in here, you can say, to begin with, just fire one and have a look and see what happens. But this is going to, conversion complete is going to happen if it's HADC1 or HADC3. So I can say if HADC is equal to the address of HADC1, do something. If the address is equal to, if HADC is equal to the address of HADC3, do something. Okay, and turn on the light or get your conversion, and you'll know if it's the internal temperature or the thermistor, depending on the result of that. Okay, so I think we're getting there. Now, let me go back to this. So we can get the conversion, we can get and it'll either be the die temperature or the thermistor. You already know how to convert the thermistor to a temperature value. You've done that before. But we need to know how to convert the internal temperature sensor. And so there must be some info on that. And so if I look at, for instance, let me go to the reference manual and search for temperature sensor. And so this is that 1750, 1800 page, and section 1310 here. I just searched temperature and went through all the different instances till I found it. And it says the temperature sensor can be used to measure the ambient temperature of the device. The temperature sensor is internally connected to ADC1 input 16, which is used to convert the sensor output to a digital value. And so we have the 40X series, so that's the one for us. When the TS ref bit must be set to enable conversion of both internal channels, supported temperature -40 to 125. It says it's plus or minus 1.5 degrees. And it's saying here's the temperature sensor going into ADC1. And it says, okay, how do we use this? To use the sensor, select ADC1 input 16. And so we've done that, and it generated it. Select a sample time greater than the minimal sample time. And so we're leaving it at the defaults right now. Set the TS ref ADCC to wake up the temperature from power down mode. Again, it's all generated for you. Start the AD conversion. Again, if you did start IT, all of that stuff is done. Read the resulting vSense data in the ADC register. That's your get conversion. Okay, so when you get to the interrupt, and if it is ADC1, you're getting the temperature back. Calculate the temperature using the following formula. Temperature in degrees C is vSense minus V25 divided by average slope plus 25, where V25 is vSense value for 25 degrees. Okay, so there's a standard value there. And then average slope is the average slope of the temperature sensor vSense curve given in millivolts per degrees C or microvolts per degrees C. So there's so you could almost just, for instance, cut that, paste it, and it's a great thing to put as a just comment in your block of code. So there's how I go about converting it. So we need to know what vSense value for 25 degrees C, V25 average slope. So if I go look at the data sheet, that's the STM32F407 data sheet, the 200-page one that just basically talks about the 407. Way down buried at table 69, it says average slope is 2.5 millivolts per degrees C. And voltage at 25 degrees is 0.76 volts. And then, so what you need to do is plug those into your formula, make everything as volts, because that's millivolts, the 2.5, make everything as volts, and that's going to take your value. What's V? If I read the get conversion, let me go back to that. Okay, okay, this thing right here. I do ADC get conversion. What do I have? What if I do, huh? Maybe I got some sort of representation. What is it in the, what, give me a typical value that would be there, you think? Anything? Yeah, well, I don't know, maybe. 0 to 4,095, right? Something, who knows? So, but, okay, so let's say it's 20. Do I plug it into as vsense? It's not a voltage, it's 20. I don't know what that is. How do I represent it as a voltage? 3.3 volts, or yeah, and divide it by your 4,095, right? We convert it to a voltage. It wants a voltage. So a common thing I see is somebody put 20 and I don't know, they have 9,000 degrees or something. And it's like, okay, that's a voltage. This is a voltage. That average slope, well, it says millivolts, but it's a voltage. Okay, change it all to the same units and make it all work. Okay, otherwise you're going to get some really kind of wonky results here. So this is a good one. This is in the RM0090, the big reference manual. And again, that's at, down in around section 13, at least in the version that I have here. So you want that, and then it references the data sheet, which is around section 5, to give you some of the information there. Okay, so you already have the one ADC. You managed to get temperatures of with it last time using the thermistor. Now we have another formula to do the internal sensor. And then when an interrupt fires, you are going to be going to that interrupt handler, the it.c file, all the way down to the interrupt handler. And again, there is another interrupt that is firing every 1 millisecond. This SysTick handler is firing. Okay, so a number of interrupts are happening. Now, we looked at this a little bit the other day. In startup, there's this startup file, and it says the startup file, it has the 407 devices vector table for GCC-based tool chains, which ours is the GNU C compiler. This module performs, it sets the initial stack pointer, and it sets the program counter for a reset handler, and it sets the vector table. Stack pointer, of course, that's where stack, when I go to jump to different functions, it's going to push something on the stack. So when I do a return, it knows where to come back from at the end of your functions. So that's set up somewhere in memory. Reset handler typically happens at 0, and then it sets the vector table with the exceptions, ISR, and then it goes to main. So it also initializes your different areas for initialized variables, uninitialized variables, all of that. So there's some assembly language stuff happening in there, and then it branches to main, and that's how it goes and calls main after it sets everything up. Your microchip pick did the same kind of thing in behind the scenes. And it says the minimal vector table for a Cortex M3. And so some of the things we looked at, there was a reset handler, non-maskable. That's in that it.c file. It has those same words. Manage handler. Let's go all the way down. There's SysTick handler. So SysTick handler, I said that fires, that's a system-wide timer, and it fires every millisecond. And when you set up the clocks, it set that up for you. And so that's there. And when you use HAL delay, it keeps track of time over there. Then, so all of this stuff can run basically without the nested vector interrupt controller being all set up. And then everything else, all of these external interrupts are handled by the nested vector interrupt controller. And so we have real-time clock wake up, we have external handlers, we have some DMA controllers. we have the ADC IRQ handler, and it says for ADC 1, 2, and 3 ADCs. So this is just a table of function addresses, interrupt service procedure addresses. Okay, and so the nested vector interrupt controller, you can set up priorities, and then it will pass the vector table location, and then it looks up where the function is, the interrupt service procedure is, and it goes to there. Okay, so it knows to go to ADC IRQ handler, and then it runs everything there. And again, as part of them helping us out, they said, hey, probably you want to get the data when you've gone there. So from a conversion from an ADC. So one of the weekly defined handlers is this conversion complete callback, which we can put in our user begin and end. Okay, so this ADC, now it used to be, again, they've set it all up for you. It used to be you'd have to go and it wouldn't generate all of that for you, and you'd have to figure out whatever they called it in the vector table and go and use it. The PC does this very same thing, a vector table. And years ago, Norton, for instance, would have a Norton undelete. And so if you installed the Norton package, it would take over the calls over to your floppy disks so that it would keep track of what you deleted. So if you screwed up, it could go and put them back. Because when you delete something off a drive, it doesn't actually delete it. It just deletes the first character in the table entry for your file allocation table. It's all still there. You just have to go put that character back. And so that's why, if you're in the drug trade and you delete everything and stuff, it's easy for somebody with some tools to go put it all back. Yep.
Can you explain .week?
Yeah, .week. So when I go over to the, where did I have it? When I go here, so this is saying they may not exist. We're putting a placeholder, but it's telling the compiler, don't give me an error if you don't find it. But it's allowing you to overwrite it with things that you define. But it wants a placeholder to say, we've thought about this. For instance, there's an interrupt, this HAL complete callback. And so if I just defined it, it could be going, hey, you said that there was a HAL ADC conversion callback, and I'll set space for it. What it does when you define a prototype is it says, you're going to call this function and it's going to return, I don't know, a float or whatever you said it was going to return. It sets aside space for it. I don't want you to set aside space for it. I want you to have the option to do that. And so this is what I've used in my APIs. And so you can define it, but it won't give me an error if it's not there. Okay, so it's expecting you to override this. And so same with when we go into our startups, we're saying, okay, all of these, I'm probably not going to use any of these. In this case, I just use the ADC IRQ handler, but it knows what to do with them if you go and use those. So over here, we have, like I say, our ADC IRQ handlers. Okay. So one of the tricks, the documentation, where is it? Here. So this is the name of the conversion callback you want to put in user defined for, but if you want to go find it, you could highlight that. Anytime I go to find this, what I did is I said, okay, ADC IRQ handler, which is in it.c, you right click, you go open declaration, takes me over to where it is. And then this one somewhere is the conversion complete callback, which you just had to find. This is right there. I just to find out. So if I go right click and I go open, and the reason I wanted to go search that is I just wanted to copy this and put it in main. Okay, in user begin for, user end for. So that will run when this interrupt fires in your main routine, and you don't have to say, hey, the variable is in this file and I need to link it over to the other file and do all of that kind of thing. Okay. And then again, the same one will fire for 1 or 3. Now let me go back to, there. and let's go to there. Okay. Oh, it's just showing it here. So not letting me send it over here. Let me go to System View, see if it does. No. You can set, it's grayed out for, I'm not really quite sure why it's grayed out, but it's going to generate code that has different preemption priorities and sub priorities. And so I can put different levels of importance. So right now, I would have to go in my code and go and set that because it's not letting me set it for some reason. But you can just leave it at default, but I can say I have other things that are more important. So as we start using the interrupts, do you want the system timer or the ADCs or the UARTs or all of that? And what the nested vector interrupt controller is going to do is it's probably actually because I only have one other than the SysTick, but it's going to then let you choose which more important. And so you can go through it and look at all the different interrupts and say, if I have this table, do this one first, then this one, then this one. That's a matter of you giving it the priorities. It's the nested vector interrupt controller is then going to give to the CPU, to the ARM chip, the word location of the next most important interrupt. So it'll look at the vector table and say it's vector 15. And so it goes down to 15, says that's the UART or whatever, and then it will jump to that service routine in the it.c file and run that. Okay, that's the ARM just gets the next one that's available if an interrupt fired to tell where to go. Let's kind of, we'll leave it there for now, and we'll continue on with this tomorrow.